the plan for the remainder of the semester, okay? So there will be 2 more homework assignments. The assignment that I will release later today is a 2-week assignment, okay? It's not that it's particularly long, it's just that, so, you know, where we are in the lecture, some of it you'll be able to do now, and some of it will require some more lectures. So it'll be 3 problems, and it'll be due in 2 weeks. And then there'll be 1 more assignment due before Thanksgiving, okay? And then it's time to start thinking about your final project. Well, let's maybe just briefly talk about the final project and what it's about. So this is something I've been doing for many years. The project is to write or substantially edit a Wikipedia page on some topic in quantum optics that will involve an experiment that was done and writing about all the theory behind that experiment, okay? The thing that's nice in quantum optics is there's so many beautiful demonstration experiments that are kind of demonstrating some very fundamental aspect of quantum mechanics or quantum optics, okay? So that's what the project will be. There are a number of motivating factors about this project. One is, well, I want you to do the research about, you know, typically it might be, you know, there's some paper or some set of papers, and it doesn't have to be one experiment, it could be a class of experiments as well, that I want you to read and try to understand and do the research on the background so that you can explain the theory behind it. That's one of the motivating factors. The other motivating factor is for you to take a look at Wikipedia and say, who wrote this crap? Is that any good? Is that actually accurate? Who's writing Wikipedia? You. And so, you know, the goal is to, you know, partially, Wikipedia has improved over the years. I think it's really actually quite good in a lot of ways, but not always. And so it's good. I think it's an important source of information that I think almost everyone uses. You guys use Wikipedia? Yeah. So
great. Some of the physics pages on Wikipedia are excellent.
Yeah. Yeah. Some are excellent.
Is it because you?
No, I take no credit. But yeah, that they were awesome.
How much of the current quantum optics Wikipedia pages are from 2 years ago?
So you know, so part of it, you know, Wikipedia is an important source of information for all of us, and I think it's important for us to understand how it's good, how good it is, and also, you know, maybe you want to contribute to Wikipedia, right? Maybe you want at some point to share your knowledge and improve it. So that's what the project will be, and so it's not to necessarily. It'll be up to you to, if you want to post it on Wikipedia or not. The plan will be to learn how to use the sandbox to write the page, and it'll be in a form that's, you know, can be looked at, and that you can send me either the link or a PDF and I can look at it. You don't have to post it on Wikipedia. That'll be up to you. Yeah.
And the Ivan Deutsch Wikipedia page is off limits for this.
Yeah, no, I'm not an experiment. Maybe I am, but yeah.
What have you inspired in?
Yeah. So
I do have a
we'll
question.
talk more. Yeah.
What if the thing we want to write about is sort of in a category of physics that already has a Wikipedia page? Would it
Yeah.
be like an entire section? Would that work?
Yeah, I mean, so then the goal would be to, you know, augment it appropriately, substantially. If what you want to do already has a Wikipedia page, then, so what I'm asking everyone to do, firstly, is send me a proposal, which is just sort of, this is what I'm gonna write my Wikipedia page about. Here is the references that I've found so far that's motivated this. You know, here's an existing page that's close, and I'll approve it or not. Okay, yeah?
We have to make sure we don't collide with other classmates.
No, no.
So we can use edit words if we don't actually publish it.
You could, yeah. So no, if you choose the same topic, that's fine. I'll also give you some suggestions, okay, of some topics.
I call zero
All right.
man on the kip sale on table.
So we'll do that. And I'll give you the sort of official assignment soon as a preview of what's to come. All right? Does that sound like fun? Yeah. Fun. Yeah. Yes.
Would we be able to get like some examples of actual projects from the last class?
Yeah, I mean, you can look at them. I think it's just easier to, you know, I'll give you topics and you know, guidelines for that. I think it's just best for you guys to just think of it on your own. All right, good. So let's continue on then with where we are. So we've been talking about states of the quantum field, of the electromagnetic field, which we can think about always as states of a multi-mode simple harmonic oscillator, quantum simple harmonic oscillator, okay? So we can particularly think about a single mode, to just get started on that, and that's just a simple harmonic oscillator, okay, which represents the oscillation of the field. And different kinds of states we've been looking at. For example, a Fock state, or a number state, is a state that is an eigenstate of the number operator, okay? And the number operator is A dagger A, and it's also an energy eigenstate of a free simple harmonic oscillator, right? With energy n times h harmonica, ignoring the 0 point energy, okay? So a Fock state has a definite number of photons. There's no uncertainty in the photons. It has n photons in the mode, okay? But it doesn't have a definite value of the oscillator. Its quadratures x and p are uncertain, and that uncertainty, actually that's the square, is given by that for the n Fock state. And that is to say, if I were able to do a measurement not on counting the number of photons, but somehow, some way measuring x and p, those are called homodynamic measurements, we'll talk about them more next semester, then we wouldn't get a definite outcome. We would get a random outcome that would be distributed according to some probability distribution, and that probability distribution is determined by, in quantum mechanics, the square of the amplitude of the x eigenstate with the Fock state, okay? And that probability distribution is familiar in wave mechanics. It's the wave function of the simple harmonic oscillator. Now, this is not the wave function of the photon, okay? X and p are not the position of the photon. They are a property of the wave, not the particle. And the particle is the collective thing, right? And this thing doesn't have necessarily one photon in it. It could have many photons in it. So x and p are not the positions of the photon. They're the quadratures of the oscillator. It's very confusing. Okay, we can talk about the momentum of the photon, but that's a different deal. All right, now we'll come back to this. And maybe I wanted to draw this somehow. I got erased. If I think about this, okay, if I think about a kind of phase space, which is not exactly correct, but we'll get to this. I can think about classically a state that has a definite energy. It lives on this trajectory. Every point on this space has the same energy classically. Quantumly, the wave function is concentrated along this circle that has a certain radius, so that the magnitude of this is the square root of n, okay? And that state has a definite amplitude, but a completely uncertain phase. We'll come back to the phase, we're gonna talk about that more now, okay? So a Fock state has a definite end, but a completely uncertain phase. We can't say what the phase of the oscillator is, okay? A coherent state is also what we call a quasi-classical state. This state has a well-defined, at least to some degree, I should have said in this case, the mean x and the mean p, in this case, the mean field is 0 in this case, whereas the mean field of the coherent state is non-zero. In fact, it is the classical trajectory. And similarly for p. So the mean x and mean p are going around on a classical trajectory, going around with an angular rotation velocity omega. And the state has a mean number of photons, which we expect classically. The square of the amplitude is the energy, and so that's what we expect. But it doesn't have a definite number of photons. It has an uncertain number of photons, and the fluctuations are given by the square root of the mean, okay? And the probability of seeing n photons is a Poisson distribution, okay? So it has a mean number of photons and fluctuations around the mean, okay? Its fluctuation has, as I say, it does have a mean field, it has a mean x and a mean p, but they're not definite points in phase space. There's fluctuations around that, and those fluctuations are equal and given by the minimum uncertainty at all times, okay? So, again, if I were to measure the x or p quadratures through a homodyne measurement, I wouldn't find a definite outcome. It would be centered around the mean point, x naught and p naught, with fluctuations around that, which are exactly the same as the fluctuations for the vacuum, okay? And so the coherent state, what we showed last time, is a displacement on the vacuum. You can think about it as a phase space. This operator we call the phase space, not distribution, phase space displacement operator. So it displaces a state that is centered at some point in phase space to another point. And the coherent state is a displaced vacuum state. So I should think about the coherent state as it has a mean field with vacuum fluctuations around it. The vacuum itself is the only state that is both a number state and a coherent state. It's an eigenstate of the number operator with eigenvalue 0, it has 0 photons. It's also an eigenstate of the annihilation operator with alpha equals 0. So it is the one state that is both a Fock state and a coherent state. Okay.
Should the P not have a hat?
It should not have a hat, absolutely not. Thank you. Yep. All right, very good. So we're talking about complementarity. And uncertainty. So x and p are complementary observables. They don't commute, okay? And that lack of commutation tells me something about symmetries and the way in which x and p are generators of certain symmetries. So the p operator generates displacements in position. I call this the position translation operator, which translates, I can think about it as something which generates a translation of x to x plus x naught. Okay, so P is the generator of translations in x, which is another way of saying is that if I have a state which is a eigenstate of x and I apply this, I will translate x eigenstate to eigenstate x plus x naught. Moreover, there's this complete uncertainty. So as to say, if I look at a p eigenstate, that, or x eigenstate, it is a completely uncertain in p. So it has, I can look at that state as a superposition of all the p eigenstates with equal weights, integrated from minus infinity. So the probability of seeing a particular, if I look at the wave function, or this might, I call this, I can think of that a particular x naught. If I looked at the momentum space wave function of this, it would be a plane wave, right? Similar, and vice versa. So there's this interrelationship here, complementary variables, complete uncertainty, and the generator of translation, okay? So we saw this uncertainty, as we were saying, we could think about, there is no way to write a state which is simultaneously an eigenstate of x and p together. It can be one or the other. We can have a state that is an eigenstate of A, and it's a kind of best trade-off. The best we can do of something which is kind of like a simultaneous eigenstate of x and p, but not exactly. It has this uncertainty bubbling around, okay? So the quadratures, quantum mechanically, the quadratures of an oscillator are always in trade-off. I can define one quadrature well, but then I'm going to lose my certainty about the other, and vice versa. The coherent state is the best trade-off we got, okay? We also know that when we think about a complex number here, yeah?
What's meant by best?
Minimum uncertainty.
Okay.
So delta x and delta p are both the minimum uncertainty. This is the best I can do. I can't make the uncertainty product any smaller than that.
Okay.
I can't shrink it anymore. And moreover, it's an equal trade-off. I could in principle have a state which better defines x and least defines p. It would look like that.
Yeah.
That's called a squeeze state. We'll talk more about that another time, okay?
So that's why it's symmetric, that bubble, is because you have equal trade-off between.
An equal trade-off, right?
I see.
So the coherent state has that equal trade-off. And it's minimum at all times. All right, so when we thought about this complex number as having it's got a real and imaginary part, or an amplitude and a phase. Classically, when we think about the phasor, then I can write it in real and imaginary parts or in polar form. This is the magnitude of A, okay? So there's a set, remember, the amplitude is the square root of the magnitude squared. So there's a kind of, remember, if we go to the quantum thing, A star A is like A dagger A. So there's some complementary relationship here as well between amplitude and phase, in the same way that there's a complementary relationship between the two phasors. If we looked at the operator that I called R, which is e to the minus I theta n hat, right? It looks kind of like this. And I look at this relation, which I can do using Baker-Campbell-Hausdorff. I find that. Which is to say, and, oh, I don't know why I call this phi. Theta. Because I guess I called it phi here. Let's call it phi. Doesn't pick a letter, any letter, and stick with it. Okay. What this is telling me is that n is the generator of phase translation. I start in some phase, and I translate along the circle by some amount. I'm translating the phase, okay? So n is the generator of translations in phase. So we might be tempted to say here, leave it there, come back to that. That there is
So sad.
so bad, so sad, okay.
There.
To say maybe there's a phase operator, which you might want to define a kind of phase operator which generates translations in n, which is complementary to n, in the same way that x generates translations in p, and p generates translations in x, that there is a complementary relation between them. Quantum it's tempting to say that. How would we define a phase operator? To define a phase operator, I want to do the polar decomposition. Here, I took what was the complex amplitude and I decomposed it into a Hermitian part and an anti-Hermitian part. That's the operator equivalent of the real and imaginary part of a complex amplitude. I can always do that, always, because I can write x as a plus a dagger over 2 with the root 2 there. And similarly for p. That's, by definition, the Hermitian part and the anti-Hermitian part of an operator. I take the operator, add as a conjugate, divide by 2, that's the Hermitian part. So that's a perfectly well-defined thing. How would I define the amplitude in phase? Well, the polar decomposition of a complex number. So let's say I have a complex number z. It has a real and imaginary part, and it also has an amplitude and a phase, right? How do you define the magnitude and phase of the complex number? Well, one way to do it is to say that r is the square root of z star z. And then the phase would just be z divided by that. Okay, so that is what one does for matrices. If I have a d by d matrix with complex entries, I can define what's called the polar decomposition of a complex matrix. So I can define, if I have a d by d matrix with complex entries, I can think about its Hermitian and anti-Hermitian parts, or I can think about its amplitude and phase as a matrix. One way, the way it's defined is the following. I would define this as, I'll call it and e to the I phase operator times an R operator. This thing is a unitary operator. Remember, a unitary operator is an operator whose eigenvalues are e to the I phi, okay? And u dagger u is 1. So it's a unimodular, just like the phase is a unimodular, this times its star is 1, u times its dagger is the identity, okay? So you should think about a unitary operator as the operator or the matrix moral equivalent of a phase, e to the I phi. All right? So what would I define this? Where R is the square root of m dagger n in the same way I did here. And then u is just m times this inverse. Assuming it doesn't have 0 eigenvalues, I can always define its inverse. That's the polar decomposition of a matrix, okay? So it seems natural I should do that for my complex amplitude. Let's try this for A. I'm going to define A as the square root of A dagger A times an operator I'll call V. Okay? So that's just what I did over here. Oh, by the way, if this is a unitary matrix, any unitary matrix is e to the I times a Hermitian operator. So this is how I would define the phase. It's the thing that generates phase, right? That's every unitary operator is e to the I times a Hermitian. Okay, so looks like I've done it. It's a way to define the phase operator, right? Where, so this is v times the square root of the number operator. Where what I mean by the square root of the number operator is in the number basis, it has this representation. Yes, Nate?
Do the phase operator and the magnitude operator commute?
No, they don't. They do not. Generally, they do not. You have to worry about the order. We'll see this in a moment as an example. So here's the square root of n. Is everyone clear? That's what we mean by the square root of n. You take the square root of the eigenvalues. And v is the thing that takes me down the ladder. Okay, so it takes, let's just check that this operator does what it should do on the basis. If it does the right thing on a basis vector, it does it on all, okay? So what happens when I write v square root of n acting on n? You guys tell me. What does this do? Square root of n eigenvalue, and then v on n gives me what? N minus 1. Is that the right answer? Yay! I have a little more hair than I used to. Okay. All right. So good. That's the right thing. So it looks like we're set. We could just write v as e to the I phi and then check that this commutation relation. There's a problem. Is this actually a unitary operator? Okay. Let's check. V dagger v is equal to sum over n prime minus 1 n equals 1 to infinity n minus 1 n, which gives me a delta n prime, which is the sum over n, like that. Is that the identity? No, why not? You're missing the zero. In fact, what's true, you can check that V dagger is the identity. That's perfectly nice. But V dagger V is not the identity. This is the identity minus the projection on the vacuum. And the problem is I can't displace n below 0. So this is what we call, if you want to be fancy, a partial isometry. Okay, it's an isometry because it maps a basis to a basis, but it's not a full, because 0 gets mapped to nothing. So what this means is there ain't no phase operator. There's no Hermitian operator that we can write that does this. People fretted about this for a long time. Yeah.
Is there a condition on an operator to make it so you can decompose it in this way? Or why?
Well, I mean, I can find, no, in fact, one can show that the only operators that actually satisfy this commutation have to be unitarily equivalent or similar to X and P. X and P are the only operators that satisfy this. I can rotate something into that, but there's no other operators that satisfy this commutation.
But I guess, I mean, why can't A be decomposed in this way like you did N?
Because, I can do this if, good question. Why did it work for M but not for this? You're right, Ed, I didn't mention it. The problem is, this is true for a matrix that's d-dimensional, where D is finite. So if I have infinite dimensions, I can always do it. Infinite dimensions is a little tricky because you have different problems of convergence. There are operators, so one thing to note, this is a little paradox. What if I look at the trace of this commutator, what is it? Well, that's the trace of x times p minus the trace of p times x, which is what? 0. But that's supposed to be I times the trace of the identity, which is infinity. So there's something kooky going on in infinite dimensions because trace doesn't exist. There are trace class operators and operators that don't have trace. And that's really the story of Hilbert space. I mean, for us physicists to call a finite dimensional vector space Hilbert space is incredibly heavy-handed. It's just a vector space, we call it Hilbert space, but Hilbert space is really about, the mathematics is really about infinite dimensions, and that's what gets tricky. Yeah. Okay, so there ain't no phase operator, so you might say, people fretted about this, oh my God, how do we define it? Yeah.
Can we do the same thing with the phase operator if we just incorporate amplitude as well?
What do you mean?
I'm wondering, like, right now we tried to get a strictly phase operator, but, we showed before that, like, alpha can be present A to the I.
Well, we can define the amplitude operator just fine. That's the square root of n. But there's just no complementary Hermitian operator that satisfies that computation relation. Yeah.
Can you still define the amplitude for infinite-dimensional spaces?
Yes, you can. Because, I mean, that operator exists. Here, I wrote it down, and it's a perfectly good operator. Okay, but this comes, I'm going to take the pin out that one time Donald said, well, but we need a Hermitian observable to talk about measurement, okay? So I want to talk about the notion of observables. So most of us, when we learn quantum mechanics, we learn that observables equal Hermitian operators. To every observable, there exists a Hermitian operator, right? I can call that Hermitian operator H. They're not the Hamiltonian. What should we call it?
Capital
I don't want to call it A because A is the amplitude.
A.
M. Let's say we have our mission operator M. Okay. M for remission. Okay. And this remission operator has eigenvalues and eigenvectors. And what we are taught is that when you do a measurement of this observable, the eigenvalues label the outcomes. And the eigenvectors tell me how to calculate the probability of finding that outcome. So the probability of finding that outcome labeled by the eigenvalue is m time with the state, if it's a pure state, or if it's a mixed state, it's that. That's the Born rule. Okay? So that's what we're taught. I can also write this as the trace of the projector onto rho. So this is a projection operator. This is the projection postulate, right? Everyone, that's how we learn quantum mechanics, right? Now, while it is true that for every Hermitian operator, there exists a measurement I can do in principle whose outcomes are labeled by the eigenvalues and whose probability distribution is determined by the projection on this Born rule, where I take the trace of the state with the projector onto that. Not every measurement is associated with a Hermitian operator. What I need in quantum mechanics, the more general notion, which we'll talk a lot more next semester, is what are called POVMs, or positive operator value measure. Now the term positive operator value measure, again, is super heavy-handed. It comes from, some, we can talk about it one second. But, no one calls it that anymore. It's just the artist previously known as a positive operator. It's now just POVM. It's just a POVM. No one even knows what it stands for. It's just a symbol. It's like Prince. What is a POVM? So what we want here is a POVM is a collection of operators which are positive. What it means to be a positive operator is to say that all of its eigenvalues, they're Hermitian operators, and they have positive eigenvalues. Okay? Such that if I sum over this, I get the identity. So a POVM is a set of positive operators which form a resolution of the identity.
Should they be positive or positive semi-definite?
Yeah, they should be called positive semi-definite, but we always call them positive. Their eigenvalues can be zero, indeed. So why does this have to do with the measurement? So these are called POVM elements. The whole set is called the POVM, okay? Such that this, and therefore, if I have such a resolution, if I can write down a resolution of the identity, there exists some measurement I can do where the alphas label the measurement outcomes. And the Born rule, which tells me how to calculate the probability of seeing that outcome, is this. Yes,
So not all POVMs are Hermitian operators,
but not all POVMs correspond to projective measurements, okay? So this kind of measurement is what's called a projective measurement. So let's back up for a minute. Is there a POVM that corresponds to measuring the Hermitian operator M? What is the POVM that corresponds to measuring the operator M? The eigenvectors. So in this case, the E sub m's are the projectors. And the sum over M of this is what? It's the identity. So the set of projectors is a POVM. It's also an orthogonal projector. That is to say, M with M prime squared is, so the trace of this projector with another one is 0 unless M equals M prime. So measurements of a Hermitian operator are one and the same with what we call projective measurements, where the POVM elements are orthogonal projectors. The POVM doesn't, in some sense, the return, I mean, you don't measure the eigenvalue, you measure which outcome you have. The outcome is, in this case, labeled by the eigenvalue, okay? However, your detector is calibrated, so when it goes like this, it's n equals 1, it goes like that, it's n equals 2. You have to calibrate that. You have different outcomes, and each outcome represents something, okay? But there are but in principle, not every measurement is a projective measurement. These operators don't have to be projectors onto individual slates, nor do they need to be orthogonal. In principle, you give me some mathematical decomposition of the identity. There exists some way of rigging up an apparatus such that every click on that apparatus corresponds to one of these alphas. And I would then calculate the probability that I'd find that alpha in this way. So in order to say I'm doing a measurement, I need to say there exists a POVM whose outcomes are labeled by the thing I'm trying to measure. In this case, what I'm trying to measure is phase, okay? And so there it is. We'll come back up here. I want to measure the phase. This operator is not unitary. A unitary operator would have eigenvectors generally that are related to the Hermitian, but I can still ask myself, let me consider, I'm going to call them, are there states which are eigenvectors of this guy? I'm going to seek that. Well, how would I define it? The way I would want to define it is something which is an equal superposition of, if this is the complementary state to n, in the same way that the position eigenstate is a superposition of all momentum states, and a momentum state is a superposition of all position states. A phase state should be a superposition of all number states. This is a natural generalization of lost it. Where is it? The translation operator. This. Right? So when I act V on it, I can check, right? Let's just act V on it. Let's see what I get. I'm gonna get the sum over n equals 1 to infinity e to the I phi n minus 1. When I do that, act that on that, it takes n to n minus 1. And now I can just relabel this. Start at n equals 0. Ta-da, that's a good state. Now, I claim that these guys by the way, these are not orthogonal. You can check that for yourself. They're not orthogonal operators. Therefore, there's no Hermitian operator for which these are the eigenvectors. Because the eigenvectors of Hermitian operators have to be orthogonal. But this guy, with a little bit of work, is this.
So
Where did you get E sub phi?
I defined it. I defined the state that is the equal superposition of all the number states in the same way that I defined the position state as superposition of all these guys.
So that's a definition statement.
Oh, right, I'm sorry. Yes, excuse me, I'm sorry. Let me. Okay, so firstly, I claim this is I claim with a little bit of work, a little bit of algebra, this is true. Okay, which means that this
it's complete.
forms a resolution of the identity. In this case, it's not a sum, it's an integral, so this is a measure, and it's a positive operator valued one, so this really is a POVM, right? This is I would call this d phi, which is to say, if I look at the trace of this with rho, this is the probability of seeing phi in that little range. Yes, you have a question?
So you're saying that it's not an orthonormal basis, but you have some completeness of your basis?
That's right.
Interesting.
I don't need it to be an orthonormal
Sure,
basis.
Yeah.
Not every measurement corresponds to an orthonormal basis. I can, in principle, this is what's known as the canonical phase measurement. And it's what we mean by the phase distribution of the system. If I wanted to say, what is the probability density of finding phase phi, having done the canonical phase measurement, I would calculate it by this formula. So let's just see if this makes sense. If I look at a coherent state, what is the probability density of phase in the coherent state? Well, I would look at the square of this over 2 pi. And that would give me, these C sub n's are e to the minus alpha squared over 2, alpha to the n over square root of n factorial. Everyone has memorized that, right?
It's my new tattoo.
Good. Awesome. I don't know, want to know where it is. All right. So this is equal to e to the minus gamma squared sum over n alpha e to the minus I phi to the n over square root of n factorial squared. So that's my probability density. Okay. Now, if you notice this sum, it has alpha times e to the minus I phi. That sum is going to have lots of oscillations unless phi equals the argument of alpha. When this thing has a magnitude and a phase, when they're equal, the sum is going to be big. When you go off of that, so it's going to be peaked near this, and we'll have some distribution. Oh, did I bring my computer? I did not. No, that's my iPad. But I'll sketch it for you. So if I look at, for the probability distribution as a function of phase, and I wanted to show you for different values of alpha, it kind of looks like this. It's peaked somewhere, where it's peaked at the argument of alpha, and it has a width. And the width, the uncertainty in this, is approximately equal to 1 over 2 times the magnitude of alpha. Okay. Let me see, make sure I'm getting that right. Yeah, that's right. Okay. Yeah.
Experimentally, since the complement to phase is number, would this manifest as just the number of clicks on a photodetector?
Well, no, that's just measuring the number. How I do the canonical phase measurement is a mess. It is complicated. There is no simple way to do, I could do other measurements that might give me some information of phase, but they won't be the canonical phase measurement. I could do what's called a heterodyne measurement, which we'll talk about more, which is kind of like trying to measure x and p at the same time, and then look at the ratio of that. But it's not the canonical phase measurement. But I want to just get to this point here, that there is a mean phase, and there's a fluctuation in the mean. And the fluctuation in the mean depends on the square root of the amplitude here, right? In fact, this is equal to 1 over 2 times the square root of the mean number of photons. So we do see there's something kind of like this, at least for the coherent state, which if this were the true phase relation, we would say that this was greater than or equal to a half, because the commutation relations tell me something about the uncertainty. The coherent state, if I come back to this picture that we drew over here, it has an uncertainty in its phase. This uncertainty bubble says this is the mean phase, but the phase is uncertain. And the bigger the mean is, the less uncertain the phase is. You see that? For the same. There is this trade-off. So often people write this down, it's an approximate. As long as my state is not so close to the vacuum where, this whole problem stemmed from what happened over here. As long as I'm far enough away from it, I can have an approximate Hermitian operator. And people often write the number phase uncertainty relation this way. It's approximately true when the mean n is very big. When I get close to the vacuum, it's not exactly true. I'd have to calculate it from the particular phase distribution I get from the canonical phase operator. But just geometrically, I can see this width here was, you know, in these units, a half. And this is the magnitude, delta phi, just from geometry, is a half divided by this. That's the radial, yeah.
Is it coherent state the minimum uncertainty for any two operators?
I don't know about I would say any two. I mean, as we were kind of talking about, there's only one pair that is actually satisfied in this canonical conjugate relation, which is X and P. They're the only ones that actually satisfy the commutator is equal to I, H bar, whatever. But I have these approximate things. So I have a hard time really trying to say any two operators, what we really would mean by that.
Like you can't just define like new like observables that
Right.
are really hard to measure.
Yeah. I don't have good answers to that. I have to think about it more carefully. But what I would say is the coherent state has all these great properties. It's minimum in all these ways. Yeah, I don't know. I don't know how to generalize that. Yeah, Nate, you got a question?
If you, well, kind of going off of Tristan's point,
Yeah.
the whole, P,
The probability?
yeah, could you make an operator for the noise?
Well, the POVM, so what quantum mechanics does for us is it tells us how to assign probabilities to measurement outcomes. If I have the probability distribution, I can calculate anything. I can calculate what the expected value is, what the standard deviation is. I can think about all the moments of the distribution. So what we mean by the noise is how do the outcomes fluctuate around the mean? That's what we mean by noise. So in some sense, this is everything. Once you have the POVM, you have a way of calculating what the probability distribution is. And once you have the probability distribution, that tells you everything about the measurement. It tells you with what frequencies you expect to see certain outcomes and how they fluctuate around the mean. Yeah.
So it peaks when each phi matches the phase of alpha.
Yeah.
How should I think of that physically? And moreover, how should I think of it when it sort of moves away from that phase? Is that like the phase?
Well, what it's saying is that the state doesn't have a well-defined phase. It has a pretty sharp phase, especially as in the macroscopic limit, when the amplitude goes to infinity, I have this thing gets narrower and narrower and narrower, and that's the picture I was trying to draw here. So what this is saying is that if I do this canonical phase measurement, I'm not going to get the same answer every time. My state, if I thought about it like this, it really is a state that has many different phases. I don't know what it is. It has an uncertainty. Yeah, Andy.
Could you draw the reason that we can't make as well of a phase operator back to the fact that it like goes from 0 to pi, it doesn't go from like negative to infinity?
Yeah, I think that's a similar. It's both things. It's the fact that the number truncates. I can't displace past 0, and also it's this finite 0 to pi, not infinity. It's a similar question if you think about in classical mechanics. I can think about canonical coordinates. Okay. I can think about x and p as canonically conjugate. If in 3D, I can think about the z component of angular momentum and the angle of rotation around that as canonical coordinates. But there's no phase operator either in quantum mechanics for the angular rotation, for exactly the same reason. There's also why there's no time operator. So H generates translations in time, but there's no time that translates in energy because the energy has a ground state.
many times where we have that quantum number like L or N, then we can't have a conjugate because we hit that lower limit.
That's correct. But throw caution to the wind. That doesn't mean that we can't measure it. It just means that that measurement doesn't correspond to a projective measurement. And we're just drilled in, unfortunately, the notion of permission operators is not about observables. The permission operators are really about, in my view, what's important about permission operators is that they are the generators of the symmetry. They connect physical space to Hilbert space. Momentum is the generator of translations. Translations happen in physical space, but we need to instantiate that in Hilbert space. And so the Hermitian operator is the generator of that. Hamiltonians generate time translation. Position, time, angular momentum, space. That's physics. Hilbert space is just a way of us. It's not the physical space, it's the way in which we can encode the mystery of magical uncertainty, the fact that things have random outcomes for reasons that are completely ununderstood, because that's just the way the world is.
Wait,
Yes.
so could you do the same thing with like the Hamiltonian and make it time? I guess.
Yes, we can talk about a POV. I mean, we measure time all the time. Right now, it's, well, we're measuring the time. How are we doing that?
Yeah.
There is something we're calling time when we do a measurement. Time elapses. There's a POVM. It just doesn't correspond to our mission operator. Yes?
Why did we, when we created the POVM, why did we care that there were eigenstates of the V operator?
Because those are the things that translate meaning.
Okay,
So the thing that is the translation then is phase.
I see.
Phase translates into N, N translates in phase. Those are the conjugate variables in the same way that X and P. That's why we define it this way. Yes?
Real lasers, they'll give me, if I do higher intensity, my fluctuations phase will go down.
Yes, it does. The fundamental. Now, there can be technical noise. It always is. My laser has a finite line width, which is to say there's some other jitter of this phase. It's not a perfect coherent state. Okay? Which brings me to my next topic. No, we're not going there. So, I said that a general coherent state was something which, was a simultaneous eigenstate of all the modes, right? So that when I applied the kth annihilation operator to it, I got that eigenvalue. But not every state of light that we see in the world, we said these were quasi-classical. They were quasi-classical in the sense that the mean values of the electric field and electric field satisfy the classical dynamics. They evolve according to, some oscillation and with minimum fluctuations in all sense of the word. But is this light that's coming out of this light bulb, or the light in this beautiful blue sky that we love in New Mexico, is it well described by this? The answer is no. This state is, the notion of coherence hasn't yet fully been defined, but all these states are coherent in terms of they have well-defined amplitudes and phase with minimum fluctuations, like a laser, or the radio waves that, you used to listen to in my transistor radio.
I talk on the radio every day.
Yeah, with an antenna and everything.
I have an entire setup.
Right.
You show them the batteries?
Right, or your microwavy oven. Those are, oscillators that are oscillating, they're putting out well-defined fields. This field has randomness in it, but that randomness is not due to quantum mechanics, it's due to statistical classical uncertainty. So natural light, like from a flame, a candle, or a light bulb, or the sun, has statistical, or I would say has classical statistical fluctuations. For example, here is the electric field as a function of time that I might draw, that might correspond to light in some way. Suppose I have a single oscillator that's oscillating, and all of a sudden there's a collision, and boom, it starts. And then boom, there's another collision, and it starts. And then boom, there's another collision. Oh, there's another collision. And then it goes a long time. And then there's another collision. And every time it collides, it starts at a completely random phase. This kind of wave train with collisions is kind of what's happening in the current here. This current is flowing. If it was just an oscillating current, it would oscillate, but every once in a while something collides with it and resets it. And I don't have one oscillator. I have an Avogadro's number of them that are oscillating in this thing. And I have the superposition of all of these guys with random phases associated with them. And so really what I would say is that the positive frequency component of this electric field is the sum of all the oscillators oscillating at some frequency, but with some random phase. So, one moment, I'll get your question. Importantly, in what we call statistical optics, the wave is a random variable. We don't know exactly what this wave is because these are random. This is my attempt at random phase of that. It's random not because of intrinsic uncertainty that we can't, we have to live with, but because we just don't have full information about when a collision happened. That's that's information that's there. We just don't got it. And because we don't have that information, we assign statistical distribution to this. Okay? Yes, no, yeah.
Would a superconductor radiate coherent?
If I didn't have collisions, absolutely, yes. So, we can think about that kind of, driving without any, collisions whatsoever, that kind of current. But, even in the presence of some resistance, if I'm driving the system in such a way that it's I can still get a pretty coherent oscillator, even, with a non-superconducting. So, one of the things, this kind of classical is what we call classical light. Okay? What I mean by classical light is that light where it's either a coherent state or it is something where I can think about it as a statistical mixture of coherent states. I can redefine this thing, let's just bring this outside here, times some alpha, where alpha is the sum j equals 1 to n of these random phases. So if I were to look at the phase plane, my alpha is the sum of unimodular complex numbers. It's that, added to 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 that. And it does some random thing, and at the end of the day, here's alpha. I don't know where it is, because it's the sum of all these random complex numbers, okay? So I don't know what alpha is. I can say something about the statistical distribution of alphas. In fact, we will in a moment. Well, we know less than 5 minutes, so we're not going to maybe get to it. But what I'm saying now is that this is a random variable, but it's a classical random variable, okay? Where it is on this phase plane is determined by these statistics. Yeah?
So previously we were using alpha as an eigenvalue for the annihilation.
It still is.
Still that.
It still is. But the problem is, I don't know what alpha is. If I knew what alpha is, then the state, I would say that the quantum description of the state would be alpha, or a pure state. This is a coherent state that has a definite alpha. It still has fluctuations, but those fluctuations are quantum. But it has no classical fluctuations, because alpha is fixed. It is a definite eigenvalue of this. So how would I quantum mechanically define the state where alpha is statistically uncertain? With a mixed state. So I would say rho is the integral of R over this is a state which has two kinds of fluctuations in it. It has quantum fluctuations, the number, if we were to count the number of photons coming out of this light bulb, it would be click, but one of the reasons it would have fluctuations because of quantum fluctuations, but also has classical fluctuations on top of that. Any state of the system that can be expressed in this way, this is a honest-to-God probability distribution, is what we call classical light. By definition, the states of the field that we're going to call classical light are states that can be expressed as a statistical mixture of coherent states. There are states of the field which cannot be written this way. Those are called non-classical light. And our goal is to be able to distinguish classical light from non-classical. That's what we're going to do in the next few lectures, is try to understand what are the natures of the fluctuations. And this kind of expression, this is known as the Glauber-Sudarshan P representation. Glauber is the famous Nobel laureate who is thought to, many consider to be the godfather of quantum optics. But Sudarshan also wrote this down, and boy, Sudarshan should have won the Nobel Prize. He was really bummed that he didn't. But in any event, what's true as well, in principle, any state can be expressed in this way, except P might be negative, or it might be singular, or ill-defined. The states where P is negative or highly singular are non-classical states. I can always write down a P representation in a formal sense. But the only states that are what we call classical light are states for which P is an honest-to-God probability distribution. Then we just say, okay, it's like the light coming out of this light bulb, or this flashlight in my pocket, or the sun, or a flame, or whatever, a lamp. That's classical light. And that classical light can always be expressed as a statistical mixture of coherent states. If it's a laser with a very well stabilized and almost zero line width, we would say it's a pure state. Even a laser is not a pure state, it would be a statistical mixture with the line width. We have different, we don't have a definite oscillators, we have some phase noise or amplitude noise on a laser. But a laser is a good approximation, if it's a well-stabilized laser, to one coherent state, okay? So we're gonna study classical light, the nature of its fluctuations, and then what are the conditions for light to have non-classical, for which this isn't the case, and that's what we'll be taking up in the next few lectures. Last question, yeah?
Classical probability distribution, that P of alpha, it reflects whatever physical sort of fluctuations.
That's correct.
So if it was like thermal, would I expect a distribution to be like a maximally?
Indeed, we're about to talk about, is exactly what we're gonna talk about, and what to do. So in this case, this is a particular model of what's called chaotic light or natural light, which is where I have a bunch of oscillators with random phases. And we're gonna find that in fact the distribution of amplitudes is Gaussian.
Can I relate it to the partition function?
We will. Yeah. We'll talk all about all that on Thursday.
The Godfather of quantum optics is such a cool name. I just imagine with the mafia music.
You gotta go kiss the ring.
I just thought of him with the mafia music.